Hey everybody, we're back to do another lesson here for Chem 30. We're moving on right now to concept B6 in our electrochemistry unit. So I'm assuming at this point that you have finished concept B5, have done the quiz, and are ready to move on to concept B6. What we're going to be covering here in this concept is we're going to revisit stoichiometry. Again, I warned you guys that that was going to come. We're going to revisit how to do stoichiometry really quickly, and then get into talking about its connection to the redox reactions that we've been working with over the last little while. So really what we're going to be looking at are redox titrations, and we're going to revisit what a titration is briefly and understand how all of that is going to work. This is also sort of the end of the first half of the unit, where we've really just been dealing with the theory behind what's going on in all of these chemical reactions, or all of these redox reactions, and how we can communicate redox reactions, how we can balance them, understanding that there's a transfer of electrons from the thing being oxidized to the thing being reduced, and so on and so forth. After this, what we're going to switch into is we're going to take everything we've done in this first half of the unit and really look at some practical applications of our understanding of redox chemistry or electrochemistry. So this will kind of end the chapter, so to speak, and move on to something new. And we're going to, for redox stoichiometry, we're going to draw in on what we learned about stoichiometry in Chemistry 20, and we're going to add on to that some of the information that we have learned in this unit, particularly with respect to getting us to the balanced chemical equation in our first step of stoichiometry. So just as a reminder before I switch the slide here, don't forget that I taught you guys last year that there are 4 steps for conducting a stoichiometry question. Step number 1 is to create a balanced chemical reaction and list your knowns and unknowns. This is where things get a little different with redox stoichiometry, because creating that balanced chemical reaction is going to require what you've learned so far in this unit. Step 2 is going to be looking at sorting your way through figuring out the number of moles of your measured substance, and we'll be using either n equals little m over big M or c equals n over v usually to do that, often with titration data to help us out. Step number 3 is going to be figuring out the number of moles of your unknown or your required substance using mole ratio, and that will be done exactly the same way as we did in Chemistry 20. And then step number 4 is going to be solving whatever the question asks us to solve, usually determining a concentration when we're doing a titration question. So just a reminder, if you don't remember how to do stoichiometry, it might be a good idea to go back to chapter 7 of your textbook and have a look at that again. Basically, we use stoichiometry to predict and analyze the quantity of a chemical involved in a chemical reaction. This section, we're often going to be calculating the concentration of a chemical using a standardized solution of some sort. So we're going to go through it again. If you don't remember, maybe take a bit of a rewind back into Chem 20 stuff in your textbook, or maybe you saved your notes, and dig through that again. Redox stoichiometry has lots of applications, both in industrial and lab situations. Here's just a couple of examples. In an industrial situation, we might use redox stoichiometry to determine the concentration of an iron sample in iron ore if you're a mining engineer. So you might have a solution of iron ore, and you're going to try to determine what the concentration of iron ions is in there, with the thought that you want to try to convert those iron ions eventually into solid iron again, or elemental iron. You might also want to monitor the concentration of products in order to be sure the concentration is what they claim, and that's more of an industrial process again, although it would be done in the lab. So you might want to figure out what the concentration of this is sodium hypochlorite, so that's the main component of bleach that does the work for bleach, or H2O2, which you guys know as hydrogen peroxide. Hospital lab technicians and environmental chemists can use redox stoichiometry to determine the tiny traces of chemicals in using various methods of titration. So that's how we might use that. The way we do titrations, remember a titration is a chemical procedure that we use to determine the concentration, an unknown concentration of some sort. It involves a burette, it involves a sample, titrant, all of those kinds of things, and allows us to determine the concentration of something that is unknown. So it is a method by which one reagent, the titrant, is slowly added to another, the sample, until abrupt change in solution property occurs, and that abrupt change is the endpoint. In Chem 20, we looked at acid-base titrations, where we used an acid-base indicator and looked for a color change. In this, we're not using acids and bases, so we're not doing an acid-base titration. We're doing a redox titration, and so what we're looking for then is trying to find a color change again, but we have to use chemicals that have strong colors so that when they are present or not present, we can see the difference. So in a redox titration, the titrant is always a strong oxidizing or strong reducing agent. We often use permanganate and dichromate ions the most because they are quite strong oxidizing agents and they're colorful. So the permanganate and the dichromate ions change color when they're reduced. For permanganate, it goes from deep purple as the permanganate ion to colorless when it turns into the manganese ion. And dichromate goes from orangey to sort of a green color as it switches from the dichromate ion to the chromium ion. Okay, so we need a color change to sort out what's going on, and these ions, because they're colorful in solution, allow us to do that. So just a bit of the behind-the-scenes theory of what goes on in these redox reactions. When the reducing agent, the sample usually, not always, is completely reacted, an endpoint is reached. This is indicated by a change in color in the solution you've created. So for example, if we were titrating permanganate ions into tin ions or something along those lines, you would have you would want to get to a point where it was colorless or very nearly colorless to know that you've hit your endpoint. All of those permanganate ions have been used up. The volume of the oxidizing agent needed to react the endpoint is the measurement of the point at which the stoichiometric quantities of the reactants have been combined. In other words, we've added exactly enough of the titrant to ensure that we've completely reacted the reducing agent or whatever the sample is, whatever we're doing it. I used to use this example here at the bottom. I just keep it in because it was the worst example of an analogy. I'm not even going to go through it. If you want a little more explanation of the sort of molecular level, what's going on in a titration, feel free to give me a shout on that one. So the titration process, we normally, if we were doing this face-to-face, I would have prepared solutions for you and we'd sit down at some point and actually do a lab. But we're not going to be able to do that, so I will hopefully find a way to replicate virtually a titration for you. It may just be as simple as I find a YouTube video somewhere to show you guys what this might look like and how somebody does it. If you want to review the titration process, which I think is a good idea, because often there are questions on the diploma exam that will have something about this procedure. It's a skill that you need to know. Go back to page 804 of your textbook, way at the end of it, and refresh your memory on how we do a titration, particularly how we read the burette, because I often see that pop up on the diploma exam. Unfortunately, we won't be necessarily able to do this online and see, you guys won't actually physically be able to do a titration, which is something that you will do in first-year chemistry courses in university in the lab portion. But you may just have to get away with fumbling your way through it, and I'm sure your EAs will understand given circumstances this year. So what I want to do now is I want to run you through a couple of examples and what those examples look like. You're going to see in these examples that we're going to follow that same four-step procedure that we've always done for stoichiometry: balanced chemical equation, knowns and unknowns, calculating the number of moles of our measured substance, moving into using mole ratio to figure out number of moles of the unknown, and then finally solving for whatever the question asks. Those four will be listed. I'm going to try something different today, and instead of trying to write on something or videotape something for you like I did on the last lesson, I've just worked it out in advance, and I'll just take you step by step through what I've written out. So I'm going to pop that first example open here, and we'll have a look at this. Let's see if I can make it a little bit bigger. Perfect. There we go. I'm going to leave it at that size just so I can see what's going on here. So we've got our first example here, and I'm going to just jump back to the example just so that I can read through. It says silver metal can be recycled by reacting nickel metal with waste silver ion solutions. What volume of 0.1 mole per liter silver ion solution will react completely with 25 grams of nickel metal? So they're giving us some information. This isn't technically a titration. This is going to be us just doing almost a review of stoichiometry, just so you guys can remember what's going on. And we'll do a little bit of the redox stoich at the beginning to get the reaction. So really the reaction is we're reacting nickel metal with silver ions, okay? And then they've given us the concentration and the amount of nickel metal we have available. So here's what I've done. Here's your first example. There's step 1, 2, and 3, and 4 of stoichiometry, and I've created our chemical reaction up here. I have the ability to annotate, so I don't have the ability to highlight or anything. That's okay. So what we started out with is nickel is reacting with silver ions, and then I'm just treating this like a single replacement reaction. There was probably, like, let's say, silver nitrate that brought the silver ions in, that solution. But we know that silver nitrate tends to be a spectator, so we're not going to worry about that at this point. So then the other thing that we've got going on here then is those nickel ions are going to turn into, or nickel is going to turn into nickel ions, and we're trying to recover solid silver. That's the whole purpose of this reaction. And so we're going to end up with elemental silver when we're done. So looking at this just quickly, nickel is turning into nickel ions. So it's going from no charge, or 0 for its oxidation number, to +2. Silver is going from a +1 oxidation number to no charge. So nickel is being oxidized because it's getting more positive, because it's losing electrons. Loss of electrons is oxidation. And over here, silver is going from +1 to 0 for its oxidation number. It means it's getting more negative, which means that it's gaining electrons, which is reduction. This change here from 0 to +2 is 2 electrons per nickel, and this change from +1 to 0 is 1 electron per silver ion. Number of electrons lost must equal number of electrons gained, so I'm going to put a coefficient of 2 in front of the silver ion to make sure that balances, which is going to require me to put a 2 over here as well. What I've filled in down here is the information that was given to us, the knowns in the question and the one unknown. So we're asked to figure out the volume of silver solution that would be needed to react with 25 grams of nickel. So I've written in my 25 grams of nickel and my concentration of the silver ion solution, which is 0.1 mole per liter. Step 2, that was step 1. Step 2, figure out the number of moles of your measured substance. If you've got mass, you automatically can figure out number of moles. Just use the molar mass, which I pulled out of our periodic table, which gives me 0.426 moles of nickel. Then step 3 is figure out number of moles of your unknown, which is this one, using a mole ratio. So I set it up, whatever you have here, so that's 0.426 moles of nickel times the ratio of what you want over what you have. So I want to figure out number of moles of silver ions. I already have number of moles of nickel. So using the coefficient 2 for silver and 1 for nickel, I get an answer of 0.852 moles. Lastly, moving down to the bottom here, step 4, I need to figure the volume of silver ions. Now that I have number of moles, I can do that just by taking, and I did my little rearranging of C equals N over V, and V is equal to N over C when we finished our rearranging of that formula. So that's 0.852 moles divided by our concentration of silver ions gives me 8.5 liters, ensuring that I've got the correct number of significant digits. There was 2 here, so my final answer should have 2 significant digits. Just put a box around the answer, like, well, I mean, you guys are handing them in virtually, so that isn't necessarily necessary. And you're done. That's how you do this. So this question, 4 simple steps. Start with that balanced chemical equation, move through the remaining 3 steps, and you should have your answer no problem. This is example 2, so I'm going to switch back to this just to show you what the question is asking. And then this question, by the way, I switched from what's in your notes. I didn't like the question that was in your notes, so if you wanted to pause at this point and just have a look or copy down what is here into your notes, you are welcome to do so. Both the question phrasing changed and the table changed. I know it's a bit of a hassle, but I would recommend if you get a chance to do that so you can follow along. So pause now if you want to do that, and I will continue on with solving this question. So the question says, a freshly prepared solution of potassium permanganate is titrated with 10 milliliter samples of 0.05 mole per liter acidic tin chloride solution. Calculate the concentration of potassium permanganate. So our goal of doing this titration is to figure out the concentration of potassium permanganate. What's included in this table is a titration table that you would set up if you actually conducted a lab. So you have initial burette readings, final burette readings, and then I've gone and filled in the volume delivered of the titrants, and then these are our endpoint colors. And I'll get into talking about this table in a second. So we're going to follow, again, still the same procedure. We're going to do those 4 steps, but the first step is going to be the hardest because we have to do some work to get a balanced chemical equation. You're not given one in here. And don't just assume that you can write this down as a double replacement reaction. I don't want you to do that, because how are you going to include, it says acidic right here, how are you going to include the acid? That tells you we need to have acid involved somehow, hydrogen ions. If you just wrote this down as potassium permanganate and tin chloride reacts to form, you're just doing a double replacement and you're missing what's going on in this reaction. Okay, so our first step is going to be really important, and I'm going to jump to that right now, and we're going to see how that works. So slide everything over, give ourselves lots of room to work. All right, so I printed off the table so that you guys can see what's going on, and I did a little bit of housekeeping first. The first thing I did is I had a look at the bottom 2 rows here, and I noticed that it says it was dark pink here, light pink for these 3. When you get a situation like this where you've got 4 trials and one of the trials isn't the same as the other, it's usually a good indication you can toss the data out for that trial. And I did that because you'll notice that the volume here is 16.9, 16.7, 16.8, 17.4. Remember, your volume delivered in each trial must be within 0.2 milliliters of each other. If they're not, throw that one out. Okay, so this one I threw out. And then my housekeeping was to take an average of these. So add them together, divide by 3, because there's three measurements here, and we went from there. That was my first little bit. Then I went up to start to create our balanced chemical equation. And all of this work right here is just step 1. Okay, so you've got a little bit of work to do. The good thing is that you guys have done this before. And this is actually, I'm using what we learned in concept B4 to solve this. So I'm listing my entities. So remembering, of course, that any ionic compound is going to dissociate. Remembering that if it says solution, water is present. And remembering that if it says acidified, hydrogen ions are present, or basic, that hydroxide ions are present. So then I listed We had potassium permanganate, which dissociated into potassium ions and permanganate ions. We had acidified tin chloride. So there's my acid, and there's my tin chloride, which dissociated, and then my water, because these are solutions that we're dealing with. Then in red, I listed OAs and RAs. So OA, 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 RA, 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 OA, RA. Okay. Then I went to my table on page 7 and I figured out what my strongest oxidizing agent was. I compared all of the oxidizing agents I had here and found the one that was highest on the top left. Okay. And then I took my strongest or my reducing agents and I compared which one was the furthest down on the right. Watch out for this one because tin is both an OA and an RA, and some people miss that. So our strongest oxidizing agent is the combination of permanganate ions and hydrogen ions, and our strongest reducing agent is our tin 2 ions as a reducing agent. Next step was to write the oxidizing agent left to right as it appears in our data booklet on page 7. So that's what I wrote out here. And then our next step was to take our reducing agent, which is going to get oxidized, so electrons have to be on the right, and I wrote it backwards. So tin 2 plus turns into tin 4 plus and 2 electrons. Then I noticed that I have 5 electrons being gained and 2 electrons being lost. Those have to be equal. 10. So what I did is I said, okay, what's our lowest common multiple? It's 10, so I need to multiply this by 2 to give me 10 electrons and by 5 to give me 10 electrons. Then I took all of that and I wrote it as my balanced chemical equation. My balanced chemical equation right here. Okay. And then there's the last step of the last part of my first step of stoichiometry. I filled in what I knew. I knew that I delivered on average 16.8 milliliters of permanganate ions, and we had 10 milliliter samples of tin 2 ions at a concentration of 0.05 moles per liter. So then, moving on to step 2, I took my number of moles. I can figure out my number of moles of tin ions because I have enough information to do that. I have a volume, I have a concentration. If I take concentration times volume, that gives me number of moles. So I took my concentration of 0.05 moles per liter, multiplied it by my volume, and I converted that volume to liters. Remember, we're always working in moles and liters, not moles and milliliters. And I got 5.0 times 10 to the minus 4 moles. Once I've got my number of moles of my measured, I can figure out my number of moles of my unknown using mole ratio. And so I took my moles that I calculated in step 2, so that's moles of tin 2 ions, multiply it by what I want over what I have. I want to figure out moles of permanganate. I have moles of tin 2 plus. So it's going to be it's 5 times 10 to the minus 4 times 2 over 5 gives me 2 times 10 to the minus 4. And then last step, now that I've got number of moles of my measured substance, I can figure out concentration of my permanganate ions. So I've got number of moles of permanganate and I've got my volume. Just calculated number of moles here, and I've got my volume up here that we measured based on the data in the table. And so I took 2 times 10 to the minus 4 moles divided by 0.0168 liters, which is my conversion of milliliters to liters, and I end up with, I kind of wrote that down wrong the first time, 0.0119 moles per liter is my concentration. So that was a lot to throw at you. What I want you guys to recognize at this point is that this is manageable. This is not ridiculous to do. You already know how to do a stoichiometry question based on what we learned in Chem 20, pardon me. All you're doing now is adding in this little piece. And usually the way I find these questions appear is like this, where you're going to be using the method we learned in Concept B4, where you have to list your entities, list them as OAs and RAs, figure out strongest oxidizing, strongest reducing. That's usually the way that we see it pop up on a diploma exam. So don't panic about this stuff. If you need help, as always, you can ask for me. The thing I wanted to show you after that second example, and that last thing is something that's included in your notes package, and a little sort of summary table I created. I'm just going to walk you through it. It's going to help you sort of figure out how to use the different sort of techniques, the different ways we've used in this first half of the unit to sort our way through redox reactions. So I'm just going to jump to that now and show you guys what's on this this table that I created. And I'm going to maybe make it just a touch larger for you so it's a little easier to see. Okay, so what we have going on here, and this is just a summary of sort of everything we've done so far. I'm not going to go through and read through everything, but I just want to explain, excuse me, what's on here. I've got just a little summary of all of the stuff we've talked about. This is kind of Leo goes Gur. Strongest oxidizing agent gets reduced. Strongest reducing agent gets oxidized. And, you know, talking a little bit about redox reactions. Up in the top right corner here is just a little image I constructed to help you figure out, you know, which way is going oxidation, which way is going reduction. Then what we have down at the bottom here are just different ways to what we've explored in B2, B3, B4, B5, and the procedures of how to do them. And just a reminder at the bottom to remember to double check your answers. Are the atoms balanced? Are the charges balanced? Those kinds of things. So use this as a bit of a summary. You could have it sitting in front of you as you're doing questions, just to remind yourself about what's going on in each question. So that's just about it. Just some reminders to remind you again, if you guys need help, find me online, set up a meeting if you need to, anything along those lines. Assignments I'm going to list in the lesson section here where I've posted this video, but you guys can work on page 598 of your textbook, questions 3 and 4, and I have a key in the resource section for that. Worksheet number 2, question number 6. Worksheet number 2 was in the last lesson. Question number 6 I said you couldn't do. You can now do it as an example. I'm also going to post another practice question onto the Google Classroom through a Google form so that you guys can question or questions, so that you guys can work those through, submit them, not for marks, just so that I can see your progress. And one of the questions will be a redox stoichiometry, so that I can see you guys work through the procedure. And then, of course, I will post a quiz in the next couple of days when you're ready for that. Ask questions as you need them. Let me know what you're struggling with, and please let me know what's working well or not. Hey, how did this explanation of the examples work? Was it better than what I did in the last lesson? Take the time to reach out to me for that. Thanks for watching, and get a hold of me online if you need it, and stay healthy.